Hello everyone. We are going to continue our discussion on the graph algorithms, and today, let me warn you first, today's lecture could be long and tedious because I have to do a lot of drawing on the drawing board, and then, well, you do have to be able to do what I show you because those algorithms will be in the final exam. I can guarantee that. So, well, today we are going to move on to solve another type of the problem, which is a single source shortest path. So the problem is, well, if we have a weighted directed graph, and then we want to find the minimum weight path from a given vertex S to another V. Okay, so that is called a shortest path. And we say that is shortest not because the number of the nodes we have to jump is the lowest. Well, we are talking about the weight of the total edges we are going to visit. Okay, so if there is only one edge connects S to V, however, that edge the weight will be 10. And in other case, we can do a few more jumps. However, we add all the weights together, and then the weight is even lower than 10. And then we will say it doesn't matter. We want to take the one with the minimum of the total weight. Okay, and well, this has a very interesting application. So, for example, if we want to plan a trip from Chapel Hill to Wilmington, and then how do we plan the trip? So you can from the Chapel Hill and you can go to Raleigh, and then from Raleigh you can go all the way down I-40 to arrive Wilmington. Or you can from Chapel Hill you go to the south side and then you reach Fayetteville, and then from Fayetteville and then you can go to Wilmington again. So there are at least two possible paths. Okay, and then if we just consider the total mileage to be the weight of each path, and then decide depending on the total mileage, the distance we are going to travel, and then we can decide which way we would like to go. Well, that is we are using the weight as the mileage. Of course, we can use the weight as something else. For example, the total time expected, because from Raleigh to Wilmington we can do I-40 the entire way. So well, since the speed limit is a little bit higher, so I suspect the travel time if we go from Chapel Hill to Raleigh and then to Wilmington might be a little bit shorter than we go from Chapel Hill to Fayetteville, and then to Wilmington. Okay, so that's the idea of the shortest path. Okay, and for the shortest path, and we have the same a similar optimal substructure. Okay, and that means, say if you want to go from the left node and say, let me call that A, and then to the right node, that is B. Okay, so if we have the shortest path from the A to B, and then this means, well, if we take a step structure or the step path between the A to B, and then we will also have the optimal step path. Okay, so let me bring up my pen here. Let me name it A and then B. Okay, so well, if from A to B, and then we have already found the shortest path, and after that, okay, if we want to do from the C to B, so if A to C and to B is the shortest path we have already found, and then from the C to B, that is a step path of the path we have found from A to B, right? And then from A to B, well, since it is already the optimal shortest path, and then the subpath from C to B, that is also a optimal substructure. So let me just use another example to show you the idea. Say, well, if we have this graph, and then, well, this is a undirected graph and it doesn't measure, and what is the shortest path from A to C? So from A to C, and you may say the shortest path is from A to B and then B to C, right? Because there are only two hops. That's wrong, because for the shortest path, we are worrying about the total weight. And by eyeballing, I can see another way, another path, even though there's one more hop, but the total weight is even lower. Do you see that? How about from A to D, D to E, and E to C, right? So that is the A to D to E to C, and then the total cost will be a 7. And by contrast, if we do A to B and then to C, and then it is a 11, right? So well, if you want to take the one with the lowest total weight, and then we want to go with the A and then D and then E and C. Okay, so we have already found the shortest path from A to C. And the next question is D to C a substructure of the shortest path of the A to C? So D to C is here, right? Okay, this means, well, D to C is a substructure of the shortest path from A to C. Okay, so as we have now, since we have the optimal substructure, this means the D to C, well, the DEC, the substructure, should also be the optimal shortest path from D to C. Is that true? So take a look. So by eyeballing, what I can see is from D to C, the cost will be a 6. So from the D to E to C, and then the total cost is a 6. Can we find something even shorter than that? Say from the D to B to C, that is a 7, right? Or if you want to try something longer, D to B and then to E and then to C and then D, E, B, C, that is a 9. So in this case, this one wins. Okay, so that's the observation. Well, from the A to C, and then we have already got the shortest path. And then based on the optimal structure rule, and then if you pick a substructure or the subpath D to C, and then the D to C is also DEC is also the shortest path from D to C. Okay, and for the shortest path, and we have another property, that is the triangle inequality. So, well, we are going to use the delta. Well, delta UV as the weighted shortest path from the U to V. And then for the delta U and V, and if we want to pick another node in the middle, and then the delta of the U to V will be smaller or equal to the delta U to X plus the delta X to V. Okay, and the reason is, well, if delta U to V is smaller, well, if it is smaller than the delta U to X and the X to V, so this means, well, if I'm giving the name A, B, and C, okay, so if C is smaller than A plus B, and what does that mean? This means if we want to go from the U to V, we should take the C because C is shorter than the sum of A to B. So we ain't gonna take the U to X and X to V because A plus B is higher than C. Or another case, how about C equals A plus B? If C equals A plus B, and then it doesn't matter, right? Okay, we can do a U to X and X to V, or we can do a U to V directly, and then they're the same thing. And then how about C is greater than A plus B? Is that possible? Yes. So if C is greater than A plus B, and then we will definitely take the path U to X and X to V, right? So okay. So if we are in the case 1, which it will be the delta value? The delta value will be C, right? Because that is the shortest path. And for the case 2, it doesn't matter. Delta can be C or delta can be the sum of A plus B. It doesn't matter because both of them are the same. And then how about the case 3. So for the case 3, which one will be the delta? And then the delta will be A plus B, right? So, depending on the which case we are, the delta UV will always be the smaller value between C and the sum of A plus B. But anyhow, this property is guaranteed. So the shortest path between U and V will be either equal to the delta of the UX and the XV, or it is smaller than the delta of the UX and XV. Okay, so is this going to be greater than? And it is impossible, because if it is greater than, and then we are going to take this part. If this is a greater than, and then this is no longer the shortest path between the U and the V. Okay, and for the shortest path, there is one thing we do have to be careful. Okay, if in a graph with negative weight cycles, some shortest paths may not exist. So, here, so if we assume that in this circle, and the total weight just for this circle is a negative value, so let me say a -5. Okay, to make the discussion easier. And we are saying we are trying to find the shortest path from A to B. And then the weight for each of the paths is 10, 10, 10, 10. Okay, so you may say the shortest path from A to B should be 40, right? Because one hop, one hop, one hop, one hop. So a total of 4 hops, and then the sum will be 40. And then that's not correct. Think about that. So if we go here, we take this way, and after that, if we do one circle, what is that? So that is 10, 10, and then do a -5. So we can get here at the cost of 15. And then if we want to go here and go here, and then we can go to the B at the cost of 35. Why? Because after arriving the node C, we do a circle here, so we reduce the total weight by 5. So originally, we say we can do 40. Or if we want to go one loop, and then it go down to 35. So is 35 the lowest? The answer is no. Why? If we go one round and then we go another round, what will happen? So 10, 10, and then 2 circles, 2 rounds, -10, and then +10, +10. So we can bring that down to 30. Is that it? No, because we can go multiple rounds inside this circle. So we can always lower our total weight as long as we are willing to stay in this circle even longer. Okay, so in this case, what is the lowest weight from A to B? The answer is, it can be -infinity, because we can always stay in this circle, right? So in this case, we can say sum of the shortest path between A and B does not exist. Okay. So before we move on and talk about the algorithms, the algorithm of finding the shortest passes, we have to understand this algorithm that is called relaxation. And for the relaxation, we have one node, node U and node V, and then the weight between the U and the V. And we are using the D to record the current upper bound of the to get to the U and the V. So that is the list of the D. And you can understand the D as the record of the current shortest path from a source to all the nodes. Okay, so if the dV is greater than the du and then plus the weight of the u and v, what does this mean? So this means, we can get the dV, get to the node V with a dV cost. And then we can get to the u with the cost of the du. And in addition, we have a path from the u to v, and the weight is the w uv. So if the dv is greater than the du and plus the weight of the uv, that means we don't know how we can get to the u. But if you get to the u first, and then we take the path of the u to the v, that is a even lower cost to get to the v. So what do? We have to update the way we know to get to the v. So in this case, we are going to assign the duv plus the wuv, the du plus the wuv to the dv. And in addition, we want to say, okay, for the v, I'm going to use u as your parent, because getting to u first and then from u to v, that is the shortest path so far. Okay, that's very dry. Let me give you an example. So for example, we say this is the u and this is the v. Okay, okay, so for now, the du is a 5. So from the source to get to the u, the current lowest cost is a 5. And then for the v, well, the dv is a 9. This means from the source to get to the v, the current known shortest path is a 9 as a cost. Okay, and then we have the 2. So for this 2, that is the cost between u and v. So what does that mean? So from the source, we can get to the u at the cost of 5. And then from u to v, the cost will be a 2. And then this means if we want to get to the v, we can first get to u, and then from the u to v, there is a cost of 2. And then we can reduce the cost of getting to v to 7, right? So that is a new shortest path we have found that we can get to v. And in another case, so dv is du is a 5, and then the dv is a 6, and then the cost is a 2. Okay, so in this case, let me write the u here and v here. Okay, so in this case, if we want to get to the v first by getting to u and then take the path u to v, so we get to u first and then go from the u to v, the cost will be 7. Okay, so in this case, we can still go from u to v, no problem. However, if we take that way from the u to v, and then the cost will be even higher. So guess what? We don't bother to update the v because the 6 is a lower cost. So we do want to take the lower cost to get to the v. So in this case, we have found a possible way that we can get to u first and then from u to v. But do we want to update the shortest path of v? The answer is no, because the current cost to get in getting to v is even lower, right? Okay, so the next part, that is a real algorithm that we can find the shortest path from one source to all the other nodes, and then that is the Bellman Ford algorithm. And as you can imagine, those are Bellman and Ford are the inventor of this algorithm. Okay, and for this BF algorithm, well, the first part, we want to initialize the D. So to initialize the D, and then we set all the cells of the D to infinity. And then for the S, we have the source. And for the source, we want to specify the distance is a 0. So from the source to get to the source, and then the cost is a 0, right? Okay, and the second part, we want to start the relaxation. So we are gonna iterate for a total of v minus 1 time. So that is outer loop. So this part is how many vertices we have, and then we do a minus 1. Okay, so we are gonna iterate for the outer loop. We are gonna iterate for v minus 1 time, and then for each of the edge in the graph, and then we want to do the relax of the u, v, and w. So for the inner loop, it will iterate for e times because we are going to iterate through all the edges. And the last part, the last iteration is we are going to test our solution. So why we are testing our solution? Well, there is always possible to lower the cost if there is a negative weight circle. Remember, so if after finishing the second loop, we want to do a further test. So in the further test, if we can still lower the cost, this means there has to be a negative circle exist. And then we are going to return a false saying, well, finding the optimal or the shortest path in this graph is not doable because there is a negative circle. Otherwise, we are going to return a true. And then for this relax, that is the relax function call. Okay, so well, I know this BF algorithm or the Bellman Ford algorithm is very dry, and well, before we see the example, let me finish the algorithm analysis. Okay, for this algorithm, let me bring up the pen again. Well, analyzing this algorithm is kind of easy. So for this first iteration, and that is the V, right? So that is the OV. And then for the second one, so the outer loop is the V. And then for the inner loop, that is the E. Okay, so for the second loop, that is the V multiplied by E. And then how about the third one? The third one is a E again, so O, E. Okay, so if we add those three parts together, and then the upper bound of this algorithm will be O V E. So V is the number of the vertices, and the E is the number of the edges. Okay, so I'm gonna pause my video here. It's already long enough. In the next video, we are gonna work on this example. Okay, I will see you guys in the next video.